Okay, in this problem, we are looking at magnetic flux and magnetic flux, area, and induced EMF as functions of time. And we are assuming that this rod here, this half circle bar, moves at a constant speed to the right. So the first thing to think about is that there are this rod, the bars here, these two half circle bars are both conductors, and so that means that there are charges that are free to move. So if there is an induced current, then what's going to happen is my positive charges are going to move in one direction and my negative charges are going to move in the other direction. So what we can do is we can figure out what direction they're going to move in, and if we can see that there's a direction that they're going to move in, then we'll know that a current will flow because we have the two bars connected with these rails, which are conductors, and so we'll create a current. So if we think about a charge that's just any charge that's on this bar, then that charge is moving to the right. So if we think about if we just pick a charge, let's pick draw and draw. So if we just say we have a charge and it's moving to the right like that, so that's like my plus Q, moving to the right, and if I put my finger in the direction of the arrow and then my middle finger, so my pointer is in the direction of the arrow for velocity, and then my B field is down into the page, then my force has to be up. So that tells me if I have a charge right here, the charge is going to move up, say over here. So I'm going to have a bunch of positive charges here and a bunch of negative charges here. And so that means that I'm going to have current that's going to flow from positive to negative. So I'm guessing my current's going to flow clockwise, but we can check and see that too from our change in flux, in magnetic flux. Okay, so let's start by finding the area. So if you think about the area, so remember what's happening is I have this second half of a circle that's a bar that's moving to the right. So I'm going to have an area here that stays a constant. So I'm going to have this area for this half of a circle, and I'm going to have this area. And these two areas will stay constant. Now, the thing that's changing is this rectangle. So this rectangle, I'm going to call this y, and we know the y is the length, or say the y is the width, and the b, this here is the length, and we'll call that length. And that length really, so my length is equal to 2 times r. So L, that length is equal to 2r, because it's twice the radius of that circle. And y is going to be increasing. So my L is going to stay the same, or 2r isn't going to change, but this y is going to get bigger as this moves to the right. And so I'm going to write that y in terms of the velocity times time, because it tells me that this bar is moving to the right at a constant velocity. So I can represent that as a velocity times time. So now if I want to find the area, I'm going to have my two circles, or two half circles. So let's just call them one circle. So we're going to call that pi r squared, plus my rectangle. And so we'll call that y times L, or 2r. And if I want to rewrite that with my little equation for y in it, I'm going to say pi r squared plus 2r, and I'll plug in for y, v times t. So that's it. That's what the area for part A, this A, I need to find the area. So we found the area. This is my area. So I'll say that's my area. And now I'm going to go to flux. So flux is given by this symbol, phi b, and the flux is just b times A. And that's because this area here is like in the plane of the page, and the B field is coming up through it, so it's not oriented at an angle or anything, so I don't have to. It is usually B dot A, which is the dot product, so it would be BA cosine theta. But since the area is perpendicular to the B field, I can write it just like that, and so I'm going to have B times pi r squared plus 2RVT. Okay, so there's my flux. The next thing is induced EMF. So I'll write that up here. My induced. Let's see, undo. EMF is given by that symbol. Epsilon is equal to negative d phi dt. So I can just plug this in, right? So the EMF is equal to a negative. And now let's look to see what in this equation for phi is a constant. So we can see like this first term, there's no t in it. So that's the derivative of that with respect to t is gonna be 0. So I don't need to worry about that. Here I have, basically this is a constant times b and then times t. So I can pull the constants out. So I can say, okay, b times 2RV, and then I'm taking the derivative with respect to t of t. And so that's just 1. So I get an EMF is equal to a negative 2RVB times 1. So that's my EMF. And so we can see that my EMF is actually, my EMF is constant. Okay, so next, now we're going to assume that the sliding rod, so let me change my, so I just copied this into a new slide so it'd be easier and would have some space. So now the rod, this rod here is moving to the right, but it's not at a constant velocity. It's starting from 0 and it's increasing, it's moving to the right with a constant acceleration. So that means it's speeding up, right? So it starts at 0 and it just starts speeding up. So that tells me that I have the same thing as before, but now my y is equal to 1/2 a t squared. So now when I want to plug that into my area, I need to find, I want to find the area, and then I want to find the flux, and that once I have the flux, then I can take the derivative to find the induced EMF. So let's find the area. I know I'm still going to have my pi r squared for the two parts, right? The area here is half, and this area is the other half, so that gives me the full circle, which is the pi r squared. And then this I know is moving to the right, so this is going to be my y, and this is going to be my L, which is equal to 2r. So L is equal to 2r. So I'm going to have pi r squared plus y times L, and rewrite that. Area is equal to pi r squared plus, so I'm going to plug in 1/2 a t squared times 2r. So a is equal to pi r squared. Now my 2's cancel, so I get, let's see, cancel that. I get r times a times t squared. Right, okay, so the next thing I'm going to do is find the flux. So the flux is just b times a. So I'm going to get b times pi r squared plus b times r a t squared. So now if I want to find the EMF, so EMF is equal to a negative ddt of the flux. And if I plug that in, I know that, again, the first term does not depend on time. So when I take the derivative, I get 0. So I just need to think about this term. So this is going to become a negative ddt of b r a t squared. And this is equal to, so I can pull out the constants b, r, a, and I'm really just taking the derivative of t squared. So that's going to give me 2t. So and I forgot the negative. So my induced EMF is equal to a negative 2b r-a-t. So that's my part B. So let's switch to the next slide. And this says, sketch and label the induced EMF for each case on the graph above. Okay, so for each case, so far that means we have an A and a B. So let's do A here. So on this graph, I want to add in a little bit on this graph so that we have the ability to go below the axis. So for the first case in A, we have A, EMF is equal to a negative 2BR2 times B times R times V. And so that's just a constant. This is a constant with respect to T, and it's a negative value, so it's just going to look like a straight line across like that. So that's A. And then B, the EMF is equal to a negative 2B ART. So this part is just a constant. All right, so I'm going to have E is equal to some constant, a negative of some like constant, which I'm just going to call this C times T. And now if I just had C times T, I would have a line. So if it was just C times T, I would have something that looks like, so this is E is equal to CT, and this is T. I would have just something that looks like this, just a line like that. But now for this case, right, it's a negative. And so what does that mean? Well, so I'd still start at 0, but I have a negative slope. So I'm going to do something like that, right? And so this is going to be B, something like a line. And I don't know exactly where they meet up, but you get the idea. It's a negative slope. It's linear because this is only dependent on T. And then these numbers are just constants. So those constants would adjust the slope right there. Okay, and next is, we'll start with D. Okay, so what D is we want to calculate the acceleration in order to have a certain current. And so let's start with, we have EMF, and EMF is just a voltage. So EMF is a voltage, an induced voltage. So we're going to have some induced voltage, and it tells us that these two bars have a resistance. So each of these bars has a resistance. This is an R and this is an R. So really, like, if I think about it, what I have is I have this and this R, which is, these two are connected in series. So I could think about it like I have some voltage, some induced voltage, and I could write it as if it was like, look like that. So I know my induced voltage. I can write my like EMF there, and then I've got R and R here. And that's just two resistors in series. So two resistors in series. So REQ, the equivalent resistance, is equal to 2R. So if I think about my current, I'm going to have current is equal to EMF divided by the equivalent resistance. And that's just EMF divided by 2R. So let's plug in for EMF. So I is equal to, and so this is the case, this is the same case where there's an acceleration. Because it's asking us what acceleration is required for a given current. So they give us the current. So let's plug in EMF is, since we don't, the negative just helps with what direction we're going. So we're not going to worry about having a negative here. We'll figure out whether it's going clockwise or counterclockwise in a minute. But we're just going to calculate the value first. So EMF is 2B ART, and that's over 2R. And I'm interested in A. I'm solving for A. So I'm going to multiply. I'm going to do like cross multiply, right? So I do 1 there. Cross multiply, I get 2B ART is equal to I 2R times I. And so if I divide everything by 2BRT to get A alone, I get A is equal to 2RI divided by 2BART. So the 2's cancel, and I'm left with A is equal to RI over BART. So A is equal to, the resistance is 0.0025 ohms. The current is 0.6 amps. B is 0.005 Tesla. Oh, I forgot. So I should not have A here, right? Let me just go back, and I can erase it here too. So I'm just going to have 2BRT, and this is BRT. So R is, they tell us, R, do I know what R is? Yes, 0.5 meters, and T is 3 seconds. And when I plug that in, I get A is equal to 0.2 meters per second squared. So the last thing they want to know is indicate whether the current is clockwise or counterclockwise. Okay, so to find the direction for the current, I want to think about flux. So I've got the B field, right, going through here. So I've got this B field. It looks like that. And this side is moving to the right. So that means that this B field is increasing. So I have increasing, oops. So I have increasing B, or increasing flux that's into the page. And so increasing B field into the page. And so remember that when I have an induced current, it doesn't want to have an increase. So it's trying to oppose an increase. So to oppose an increase, it needs to create a B field out of the page. So it wants to create B field out of page. Right? So it wants to create dots in here, right? So it's out of the page. And so what happens then to create a B field out of the page? Then we put our thumb in the direction of the B field out, and our fingers curl around, and they're curling this way. Right? So that tells me that that the current is counterclockwise.